I just wanted to go over a little review of Jamovi, which is a good alternative statistics package if you want to do analysis. The good thing about it is it's free, you can just download it. It's actually a graphic user interface for using the R programming language, but we don't need to go into those sorts of depths. But it's a step forward to using R if you want to go into full data handling. The thing that makes Jamovi powerful is that you can add extra functionality to it, and you can see this through this button here which says plus for modules. Now I've added one already, which is this major module, which is for meta-analysis, because that's something that I often have to carry out or to help people to do. Another module that's added is the scatter one, which has better diagrams for scatter plots and Pareto charts. Jamovi has quite a clean and simple interface. The menus across the top, you have the first thing which tells you about the program, and it's got how to open your files, and you've got save and save as and export. So save as is going to be saving things which are the proprietary functions of the particular program, whereas export means you can save to different file types which can be put into other programs. For example, things like Excel files. You've got the variables windows, which we'll come back to when we've actually opened a data set. You've got data, which allows you to actually input the data and do specific functions on it. You've got analysis, which has these buttons doing the most important kinds of analysis you're going to do. Exploratory data analysis is exploration, t-tests. ANOVA, regression. So this is hypothesis tests about means. Hypothesis tests about means when there's more than two groups. Regression is fitting lines. Frequencies is chi-squared tests, and you can also do factorial analysis. And there's edit there, which allows you to add markup and add other things that you might want to add to your particular data set to give you more information and a richer data set to look at in the future. Because there's nothing worse than coming back to a set of data and going, oh, what did I do there? So adding content is never a bad thing. So what I'm going to do is open a simple data set. I'm going to go for open, and in the folder that I'm particularly in, my downloads folder, I have 3 sets of data. Coronary heart disease, which is a SAV file which comes out of SPSS, and these other 2 are .csv files, which is comma separated variables. And I've got the Irish dataset and I've got a sugar beet dataset. I'm going to open the sugar beet dataset because it is just a dataset containing a single variable. So if I click on that, the data comes in. So there was a flicker there as the dataset was loaded and it restarted the interface, and it's taking me back to analysis. So if I look here, it's a dataset which only contains really 1 column of data. It has a second column, but that's just the number for each of the particular data points. So when the data points were created, it just contains a list numbering each of them. And beside it, you have sugar column. So this is a sort of continuous variable which tells you the percentage of sugar found in different sugar beet plants. This data set was collected in the end of the 1800s, so in the 1890s, and it was published in quite an important textbook, and it contains 42,997 data points. If you actually read the textbook, they said there was only 40,000 points, but we'll give them these extra ones. Now I said about going to look at data. So if I click on the data, if I click on variables, sorry, I've got 2 columns. So I've got A and I've got sugar. So what I can do is look at the A column and I can put in what it is. So that's really the index of the data. Now if I go to the sugar column, what does that contain? That contains the percentage sugar content of the plant. So I can put in more information. Now, the more information you have in your data set and the richer your data set is, the easier it is for somebody else to understand it in the future, and the easier it is for you to understand it when you need to come back to it later, if you ever need to come back to it. So I would always suggest adding as much as possible. Now, looking at these variables as well, you can see here that this has a symbol beside it, which is a ruler, which is telling you that it's a numerical thing. Now, strictly, if it's got a ruler beside it, it should be a continuous variable. Integers are allowed as well, but let's think about them as continuous measure variables like height and weight and things like that. Technically, they can have any number. If I actually go back to looking at the data itself, it can't have any number. I've got ones which are 12%, and if I scan down quite a long way, I've got ones which are 13, I've got the ones which are 12.5. It goes up in steps of 0.5%. This is the precision of the experiment. That is the level to which they measured it. They could have measured it to the nearest 0.1%, but they measured it to the nearest 0.5%. Depending on what equipment you have, depending on when the data was collected, depends on this level of precision that it will be recorded. And that is important because you can't go beyond the precision of your data. So when I do anything about analysing this data, when I report my answers, I should not give more decimal places than it was actually recorded to. So in this case, it's a bit of a fuzzy thing because you have one decimal place, but really it's only recording 0.5 or 0 at that particular position. So it's not recording to any decimal places technically, but we'll take it to one decimal place. First thing you do with any set of data is you explore it and have a look at it. So you carry out some descriptive statistics. So in Jamovi, I've got these two variables, one which is meaningless because it's an index, and the one that I've got is called sugar. So I put sugar into the variables and it gives me in this other window the descriptive statistics. It says there are 42,997 rows of data. The mean value is 15.2, the median is 15.5, the standard deviation is 1.11, the minimum is 12 and the maximum is 19. If I want to do something more sophisticated, I can go over onto this left hand side and I can look at the statistics tab. So I can click on the arrow and I can choose more things to do. So I can work out things like the skewness of the distribution, its kurtosis. So skewness is how much it has a tail to either the left or the right. Kurtosis is how flat the distribution is when compared to a normal distribution. So if it looks like a bowler hat, so the top of the bell-shaped curve has been squashed down, then it's called platykurtic. If it's been stretched up, this is called leptokurtic. I can also check to see if the data is normally distributed by doing a Shapiro-Wilk test. I can cut out data that I think is extreme and different to what I expect as outliers. I can look at the range of the data, I can look at the interquartile range, I can calculate standard errors of the mean, I can calculate confidence intervals. So the confidence interval goes from 15.2 to 15.2. It's a very sharp confidence interval because of the size of the data set. The interquartile range is 1.5. And the Shapiro-Wilk test says that there's not available. Not quite sure why it's saying it's not available on that, why it would be overloaded, but that's the way you go. To be honest, I don't like statistical tests for normality. It is a lot better to do something nice and simple, which is a histogram. So as well as being able to choose those options within the statistics settings, you can also click on the arrow on the left hand side and choose the plots you want to do. You've got histograms, you've got density plots, and you've got box plots. It's not really appropriate to do a bar plot of this particular one. You can do a violin plot if you want one of those, because they're a bit fancier than doing the standard box plots. And you've also got a QQ plot, which is the best way for testing for normality. So if I look at the density plot, because this data is all grouped around measurements at 0.5, you've got a peak for each one of them. So when it's drawn the density, instead of just drawing a plain histogram underneath, it's made it a bit, it's added those extra peaks on each one of the values. So if I just do the histogram, this looks perfectly fine. There is perhaps a bit of skew on this low end, and they did actually truncate it to remove all the data which was below 12%. This is the box plot. So let's get rid of the violin from around it. So this is the box plot. So it's showing there are a few outliers. So the ones that are at 12 and the ones that are at 18.5 and 19 are outliers. The line across the center is the median. The line at the top of the box is the third quartile. The line at the bottom of the box is the first quartile. So the middle 50% of the data is contained within this blue box. If I turn it into the violin plot is an alternative way of doing the box plot, which shows, like the histogram, rotated around that axis and done as a mirror image to show you the distribution of the data. Because the data is not smooth here and not properly continuous, the violin plot doesn't look very good in this particular case, so I wouldn't use it. And then you've got the QQ plot. So the QQ plot tells you, following this line, where the data should be. Now, if the data is correct and following the normal distribution, it will sit along this line. If there's some curvature off the line, that means it's not perfectly normally distributed. And in this case, surprisingly, there is a bit of a curvature. But again, this is hard to do because it's not properly continuous data, because they measured everything to that only a 0.5% difference, which causes an issue. Just wondering about, you can add the mean to the box plot, which is nice. So the mean and the median are not exactly the same. In a normal distribution, the mean and the median will be exactly the same. So this is another thing suggesting there is some deviation away from normality. And probably, yes, looking at it, there's a skew to being down. There's a skew to this side, towards the left-hand side, which is actually fairly unusual in data.